In this video, we are going to discuss about Saytzeff Rule. In some book, you can find some other spelling, but I don't bother much about that. Saytzeff. So this rule, it is used to predict the major product in elimination reaction. For example, I go for this halo compound. Now, this can eliminate HBr to give two different products. The first one, this H may fall here and we may get a product like this. Another possibility, one hydrogen from this, I write like this, CH2H. This hydrogen may fall, we may get product like this. Which one will be the major? In order to predict that, we use Saytzeff rule. The olefin which has more substituent will be the major. Let us consider this olefin and this. This has 3 substituent, 1, 2, 3. So this will be the major product. Here there is only one substituent. Remaining there are 3 hydrogens as such. Here only one hydrogen is there. So this will be minor. What is the reason? It is very simple. It is the stability of olefin. Tri-substituted olefin, I go for tetra. Tetra-substituted olefin is more stable than tri-substituted. Tri-substituted olefin is more stable than di-substituted, which is more stable than mono-substituted, that is more stable than ethylene. So that is unsubstituted. So because of that, this is more favored than the other one. If you go for rule, you may tend to forget, but try to understand. Tetra substituted olefin is more stable. Highly substituted olefin is more stable. So that is formed. When we discuss about that, we have to also discuss about Hoffman product. It is just opposite of Saytzeff rule. According to Saytzeff, the highly substituted olefin is the major. But in Hoffman product, we go for less substituted olefin. For example, I go for the elimination of this compound. So basically, it is nothing but co-elimination. N-oxide. Now, this N-oxide can take this hydrogen as well as this hydrogen. If it takes this hydrogen, we will get this product. If this hydrogen is taken by this O minus and it falls here, what we get is like this. Earlier, we have seen that this olefin is less favored according to Saytzeff, and this is more favored. But according to Hoffman, this is more favored. What is the reason? Saytzeff, he focused on the stability of the olefin. But in Hoffman, we go for steric hindrance also. Even though this olefin is highly substituted and this is more stable, since this group is bulkier, this may not be able to take this hydrogen, which is again bulkier. So this product may be less favored. On the other hand, this hydrogen, it is sterically less hindered. So this is subtracted by this O minus and we get this product. So here we go for steric hindrance between the N oxide and the beta hydrogen. But Saytzeff, he focused only on the stability of olefin. When we discuss about that, I have to talk about a very popular rule, that is Brett's rule. What is that? Consider this compound. If I add base, will I get this olefin or this olefin? The answer is you won't get both olefin. So that is given by Brett's rule. What is that? It is not possible to generate a double bond or carbocation at the bridgehead carbon. Basically, bridgehead carbon is this one. We use the term in bicyclic compound. So it is not possible to generate carbocation here or double bond by elimination. When the bicyclic size is very small, if it is big, then it is possible. But in this particular case, since it is 2 to 1 bicyclic system, it is not possible to generate double bond here. Also, you cannot generate carbocation. Even though it is tertiary bromide, it won't form carbocation. The nucleophilic substitution will not go through carbocation mechanism. What is the reason? It is very simple. If you go for this double bond or carbocation, this particular carbon will be planar. But that is not possible to become planar in this bridgehead. If there is not connected, then it is easy. When you go for bicyclic compound, these three groups will be pyramidal shape. It cannot become planar. So that's why it is not possible to produce carbocation here or alkene here. So that is basically Brett's rule. When the cyclic system becomes too big, that is, here I add 2 more, here I add 3 more carbon. In such case, it is possible they can align, they can arrange themselves and they can become planar. So that is basically Brett's rule.